everybody? It's the 10-Minute Tutor today, and we're back for another video on physics, and we're going to be talking about work and potential energy. So this video is a continuation of our physics series. Be sure to check out our previous videos if you have not seen them, and if you're curious about other topics, we also have videos on biochemistry, chemistry, and mathematics, so be sure to check that out. Without further ado, let's get started. So, what is work? So work, in my book, is a force acted upon that causes displacement. So work has the two words of force and also displacement. So it is a force on an object that causes displacement. So it must have the components of force and displacement. So a simple way to imagine this is by no means a good representation, but picture this is a horse here. Okay, and here's the head, and there's the tail. And just like in the old days, imagine the horse is towing a plow through a farm field. So the horse is moving in this direction, and this is its initial position, and this is the final position. And as the horse moves in this direction, using its legs, the plow is going to be moved across the field from the initial point to the final point due to this force. So in this situation, this would represent work because there's a force acting on the plow that would cause a displacement. So that's just a simple way to look at it. And so I'm going to show a couple examples right now, and we're going to see if they qualify as work or not. So before you come up with the answer, if these examples are work or not, you want to identify the force first. What are the forces in each example? So for the first case, say you push against the wall as hard as you can. So here's a wall here, and there's a person right here. And they are pushing as hard as they can against the wall right here. They're really pushing against that wall. Would this represent work or not? So this is actually not going to be work. The reason this is not work is because you're pushing against the wall, but the force that you're using against the wall is not causing any type of displacement, right? You're not able to move the wall. So there's no displacement in this example. No displacement, no work. It's very simple. Okay, so another example that we can look at. Say a rock falls off a cliff. So we have a cliff here. A rock is falling off a cliff due to the force of gravity, or force, equals mg in this case. So the rock is falling down off the cliff. Is this going to represent work or not? So this actually would represent work. The reason is because there's a force that is acted on the rock that causes a difference between the initial position and the final position, which is indicative of having displacement. And displacement and force means work. Now, a final example to look at is, imagine you walk with a pile of books at a constant speed across the library, right? So here's a person, you're carrying a whole bunch of books, and you're moving across the library with these books. Now, would this represent work or not? This actually would not represent work. It's a little tricky, but the reason this does not represent work is because although you may think the books are being displaced, they're actually not. The reason is because the force is between the hand and the books, right? There's a force over here where the person is acting. And it's like you pushing against the wall all over again. There's no displacement being caused by the hands on the book. So therefore this would not represent work. Okay, so now we're going to talk a little bit more about the specifics of work in terms of the equations used in physics. So the general equation that's used in physics is work, or W, equals F times D times cosine theta, where F is going to be your applied force, D is going to be your displacement. It's going to be measured in newtons, measured in meters here. Sorry if I sound really bad, I'm kind of sick. And the cosine theta I'm going to talk about on the next slide. So the cosine theta is going to be the angle between the force and displacement vector. So if your force vector is like this, and your displacement vector is like this, cosine theta would be 90 degrees in this example, because cosine theta is the angle between the force and displacement vector, which is 90 degrees in this case. So just to go over some short examples on that, say your displacement vector is going in this direction, and your force vector is going in this direction. Your theta is actually going to be 0 degrees in this case, because the angle between the two is 0 degrees. There's no angle. So that's just one example. Now, another example to look at is, say your displacement vector is going in this case, and your force vector is going up like this. So the difference between your force and displacement vector is clearly going to be 90 degrees. So theta is going to be 90 degrees in this case. I just thought I'd take a minute to explain this because it's a very important part of getting the equation right. So I'm going to go over a set of problems, and it's important before you look at the problem to understand what force is causing work in each problem. What is the applied force? So with that in mind, here's problem 1. So a 50 Newton force is applied to move a 10 kilogram object with a horizontal distance of 5 meters at a constant speed. So here is your 10 kg object, 10 kg, and there's 50 Newton force acting on it this way, and the displacement we said was 5 meters. So now to solve work using the equation W equals F times D times cosine theta, you simply plug in the values. So work would be, your applied force is 50 newtons in this case, so 50 newton, 5 meters, and your displacement is going to be moving along with the object, because the displacement is also going to be going in the same direction as the applied force. So there's actually no cosine theta in this example. So your work is going to actually be 250 joules. I forgot to mention that when you multiply, joules is going to equal newtons times meters. So work is measured in joules all the time. Okay. Now another example that we can go over is going to be here. Okay, so now for problem 2, it goes as a 100 Newton force is applied at an angle of 45 degrees to the horizontal to move a 20 kilogram object at a constant speed for a distance of 5 meters. So now to solve this problem, we want to first draw the box. So it's 20 kilogram box, and there is a force of 100 newtons at an angle of 45 degrees. So this is your 100 Newton vector force here, at an angle right here of 45 degree angle right there. So now in order to solve this problem, work equals F times D times cosine theta, right? So let's bring it over here. So work is going to equal, our applied force is 100 newtons, so that's the force that is causing the work, so 100 newtons. The displacement we said was 5 meters, so 5 meters. And then there's a cosine theta of 45. So plugging this all into the calculator would give a work of 263 joules. 263 joules, just to round it out. So that would be the work in that example. Okay, let's see. We have another problem here. It says that 10 Newton frictional force slows a moving block to a stop after displacement of 5 meters to the right. So here's your block here. There was a 10 Newton force in this direction. 10 Newton force in this direction, and there's the object weighs 2 kilograms. So with that being said, the F gravity is going to be 20 newtons, and your F norm is also going to be 20 newtons. And when you're looking at this, the frictional force is actually slowing it down. It's acting in the negative direction. So when you solve this equation, anything in these directions, either here or here, you actually is negative work. Meanwhile, up here and up here is positive. You don't have to really put the plus sign. You just have to know that in terms of work, it's kind of like up and to the right is positive. It's like looking at a graph. We know that it's negative over here, and it's also negative below. It's very similar when you're looking at work. So with that being said, you plug in the equation, work equals F times D times cosine theta. So work is going to equal 45 newtons. Work is actually going to be equal to, we know it's 10 newtons, but it's going to the opposite direction. It's going to the left, so it's negative 10 newtons actually. It's negative work times a distance of 5 meters we said was the displacement. And that would actually, the cosine theta is going to be 0 because the force, the vector for the force and the vector for the displacement is, there's a 0 degree difference. So with that being said, you don't need to write cosine theta, and your work would be negative 50 joules in this example. Now, one last problem, a 5 kilogram object is sliding at a constant speed across frictionless surface for a displacement of 5 meters to the right. So we have our object here, a 5 kilogram object, right? So the F norm is going to be 50, and your FG is also going to be 50 newtons, and it's sliding across the constant speed. So when you solve this equation, we know that there's actually no work, because since the object was sliding at a constant speed, there was no applied force in this example. So these two forces, the Fg and Fn, cancel out each other, and there's no applied force. So if there's no applied force, there's no work.